Thanks everyone for coming out. My name is Jon Bauman. I work for the Rust Foundation, where I lead the C++ interoperability initiative. The Rust Foundation is an independent nonprofit organization dedicated to stewarding the Rust programming language and supporting Rust communities worldwide. This is a rather short talk, so I'm going to skip my bio, but you can find me later, ask me any questions you like about my background. One thing I would like you to know before we start is a key principle that motivates all my work. I believe that technology exists to improve the lives of humans. So this talk focuses on problems that Rust was designed to address in response to decades of experience with C++. And while many organizations are transitioning new development from C++ to Rust, both languages are going to be used for the foreseeable future. So even though I work for the Rust Foundation, I know it's essential to work to improve both languages, since all people are affected by the systems which use them. It's impossible to live in the modern world without being impacted by financial systems. And though Rust and C++ have myriad applications, what's most relevant to this audience is their prominence among high-performance languages and their differences' profound implications on security. First, what do I mean when I say high-performance software? For financial systems, this usually means maximizing throughput or minimizing latency. The more transactions the system can handle per second, and the less time that passes between initiating an order and completing it, the greater the competitive advantage. In cases where work is relatively simple, custom hardware may be employed, but for complicated systems with evolving requirements, software provides greater flexibility while still achieving high performance. Though there are still cases where assembly as language is used, most modern high-performance software is written in high-level compiled languages, which are more portable and maintainable. For domains where performance is essential, such as operating systems, games, cryptography, and some financial applications, a subset of high-level languages called systems languages are used. Fairly few are actively used today, and the main ones are C, C++, Rust, Swift, and, debatably, Go. These languages provide more direct access to the underlying hardware, including the ability to manually manage memory and perform memory-unsafe operations, which raises the question, what is memory safety? Memory safety can be defined as freedom from classes of defects, such as buffer overflows or use-after-free bugs, but more generally, I think you can understand it to mean that memory-safe code can only access locations that are intended storage for a valid object with appropriate permissions. To give a few examples, this means that you can't write to a read-only object, you can't access the memory outside objects you have access to, and you can't access memory allocated to an object before it's been initialized or after it's been destroyed. However, I think it's more valuable to understand that memory safety is fundamental to eliminating undefined behavior. Undefined behavior, often called UB, means the language makes no requirements at all about the behavior of the program. Now, this may seem like a strange thing, but without it, there are certain performance penalties which would be unavoidable. Consider accessing an element of an array. Since both the size of the array and the element index may not be known until runtime, for the compiler to guarantee well-defined behavior necessitates both storing the size of the array and checking that the index is not too large. But this entails a performance penalty, and since the programmer may be able to guarantee that the access is safe, systems languages provide facilities to do such unsafe things. Furthermore, this frees the compiler to assume that any behavior which would be undefined behavior must not happen, which allows for many types of optimizations. So let's look at a simple example in depth. Consider this Rust function. It takes an array of 32-bit integers and returns the element at the midpoint. This is a common operation, so making it as fast as possible is really important for performance. Line 2 returns early in the case of an empty array. Otherwise, line 3 calculates the index, and line 4 returns the element of that index. This may seem like an optimal solution, but because default Rust is memory safe, there's an automatic bounds check when we access the array on line 4. In a memory-unsafe language, such an operation could be undefined behavior if the index was out of bounds. But in Rust, it would terminate the program. While abrupt termination is safe, it's not ideal. So we could instead write it like this. Now, line 4 uses this get function, which returns some value if the index is valid or none if it's out of bounds. Since we already checked that the array is not empty and our calculated index must be less than the length, we can be sure that line 6 is impossible to reach. The unreachable unchecked here tells the compiler that if it could get to that point, the program contains undefined behavior. And because you can't have undefined behavior in default Rust, we must explicitly annotate it with the unsafe keyword. This results in the compiler transforming the get call to something like this. Line 4 checks that the index is not out of bounds, and line 5 accesses the array directly. And because the else case is undefined behavior, the compiler is free to assume that it never happens. This means that the entire conditional can be optimized away, which leaves the direct access with no performance penalty. The need to create these kinds of unsafe optimizations is why undefined behavior typically only exists in systems languages, like C++, as well as the unsafe mode of Rust. In this example, the undefined behavior was related to memory safety, but that's not always the case. Though we can't avoid it completely, when it comes to software defects, undefined behavior is the real problem. In some languages, common types of undefined behavior other than memory safety include integer overflow and dividing by 0. But regardless of the cause, in many cases, undefined behavior can lead to severe consequences. Here are just a few examples of especially dramatic impacts. The Thorac-25 radiation therapy machine was involved in at least 6 incidents where patients received massive overdoses of radiation, leading to severe pain, disability, and in some cases, death. Like most complex safety-critical systems, these failures were the result of multiple cascading defects. One notable problem was a variable designed to bypass safety checks when set to 0. But rather than setting it to a fixed non-zero value in normal operation, the software incremented it, eventually causing integer overflow and via undefined behavior, unintentionally resetting it to 0. Another example of system failure on a much larger scale is one that I remember experiencing personally. The Northeast blackout of 2003 was a power outage affecting the US and Canada. At the time, it was the second most widespread blackout in history, affecting 55 million people and contributing to almost 100 deaths. Again, failures of this magnitude are complex, but a significant contributing factor was a form of undefined behavior called a race condition in the energy management system. This kind of undefined behavior related to concurrency can be exceptionally difficult to find and diagnose. And finally, I imagine everyone in this room remembers this last example. Less than a year ago, the cybersecurity company CrowdStrike distributed a faulty software update causing serious disruption to millions of systems worldwide. Security consultant Troy Hunt, creator of the website Have I Been Pwned, described it as the largest IT outage in history, and financial damage has been estimated in the tens of billions of dollars. And like the previous examples, this was a complex failure stemming from multiple defects. But according to CrowdStrike's own root cause analysis, point 2 was an out-of-bounds array access. In other words, memory unsafety. And since memory safety is often at the heart of these issues and undefined behavior is a fairly obscure concept, the recent focus has been on discouraging the use of memory-safe languages. The unanimity of the call across industry, government, and even academia has been quite remarkable. Just to quote a few, Google has written numerous articles in this domain. In last year's technical report, Secure by Design, Google's perspective on memory safety, they wrote, "Research shows that memory safety bugs are widespread and one of the leading causes of vulnerabilities. Those vulnerabilities endanger end users, our industry, and the broader society." They go on to write that memory safety bugs are responsible for approximately 70% of secure vulnerabilities in large C and C++ code bases. And Microsoft has echoed this finding, writing, "The root cause of approximately 70% of security vulnerabilities are due to memory safety issues." Similar findings have been reported in analyses of Apple products, as well as open source projects, such as Firefox and Ubuntu. In terms of response, the Linux Foundation's own 10-point security mobilization plan has at number 4, eliminate root causes of many vulnerabilities through replacement of non-memory safe languages. Moving on to government recommendations, the US National Security Agency writes, "Inherent protections offered by memory-safe software languages can prevent or mitigate most memory management issues. NSA recommends using a memory-safe language when possible." And the US is not alone. In a joint statement including the governments of the UK, Australia, New Zealand, and Canada, Their conclusion is that the most promising path towards eliminating memory safety vulnerabilities is for software manufacturers to find ways to standardize on memory-safe programming languages. Even academia, which is typically less involved in policy recommendations, has made a strong statement. In communications from the Association for Computing Machinery, the world's largest educational and scientific computing society, 21 co-authors, spanning academia and industry with expertise in memory safety research, deployment, and policy, argue that standardization is an essential next step to achieving universal strong memory safety. They write that memory-safe vulnerabilities have persistently made up the majority of critical security vulnerabilities over multiple decades and have affected all mainstream software ecosystems and products, and that these problems are almost entirely avoidable by using recent advances in strong and scalable memory safety technology. So, what do we do? Hopefully by now, you all agree that memory safety and other forms of undefined behavior are pressing issues for us all, and especially when it comes to high-performance software. If we accept the wisdom of experts from government, industry, and academia, how do we address these risks? Well, fortunately, the vast majority of programming languages today are memory safe, either entirely or by default. In general, if you can meet your needs with Python, Java, C#, Go, Swift, Ruby, Rust, or many others, your code will be free of a broad class of the most serious defects. But this talk is about high-performance software, so some of these languages won't be the complete answer. It's the case that few programming tasks require memory-unsafe techniques for performance, and it's commonly understood that 90% of execution is spent in 10% of the code. So limiting memory-unsafe programming to performance-critical areas reduces risk by an order of magnitude and facilitates greater scrutiny of the riskier code. In the case of C++, the necessity to use memory-safe techniques for performance leads to greater risk everywhere, since codebases with multiple languages are more complex, and C++ lacks a memory-safe mode of operation. Most modern languages are safe by default, but support explicitly declared unsafe operations. This provides the simplicity of a single language while improving auditability. But that still leaves the hardest question of them all. What to do about the billions of lines of C++? Decades of effort has resulted in code representing trillions of dollars of value stored in C++ codebases, which are subject to many kinds of undefined behavior, including memory unsafety. It's not feasible to rewrite it all, but fortunately, there is some good news. Research shows that vulnerabilities are far more likely to occur in new code, even when written in an unsafe language. The longer code lives, the less likely it is to contain vulnerabilities. Significant measurable benefits have been achieved through the adoption of memory-safe languages for new code and replacement of subsystems that interact with untrusted input. However, for these hybrid approaches to be successful, ergonomic and high-performance interoperability between C++ and memory-safe languages is essential. This is where the Interoperability Initiative aims to help. There are many ways to use different programming languages together to solve problems, and many of which are flexible and language agnostic, such as inter-process communication, or IPC. But that comes at a performance cost. In high-performance software, the overhead may be unacceptable. So the C++ Interoperability Initiative is focused on so-called foreign function interfaces, or FFI. This is when compiled binaries from different languages are linked together and call each other's functions directly. While the details of this are quite complicated and interesting, the upshot is that while this is feasible today, it tends to be inconvenient and error-prone. Various libraries exist to make it easier, but due to differences in the languages and historical lack of focus on this kind of interoperability, there are limits to what libraries alone can achieve. To improve this situation, the Interoperability Initiative is pursuing 3 concurrent strategies. In the short term, we seek to improve existing tools and address tactical issues within the Rust project. In the longer term, we look to evolve Rust by building consensus around goals to change the language for better interoperability. And also, we're reaching out to cooperate with the C++ community and standards committee to improve interoperation for both languages and to help realize the mutual goals of safety and performance. In the years since the initiative began, most of the focus has been on the latter 2 strategies, and I'm happy to report there's been significant progress. On the Rust side, work has begun with the Rust project language team to investigate interoperability goals, which are currently impossible to support in external libraries. And on the C++ side, the Rust Foundation has joined the ISO Standardization Committee and found there to be significant interest in improving interoperability as well as the safety of C++ itself. Finally, at the Rust Project all-hand meetings last month, we organized the first ever face-to-face meeting between members of the Rust Project language team and the C++ committee to discuss how the two languages can cooperatively evolve to overcome interoperability challenges posed by their differences. I'm excited about the progress that's been made so far, but language evolution is slow, and interoperability is a broad and complex topic. This will be an ongoing effort for years to come, and if you use C++ or depend on tools that do, we need your help. So, how can you help? For one thing, you can become a member of the Rust Foundation. Like the Linux Foundation, we're a nonprofit trade organization, and our funding comes from membership dues and targeted donations. Your support allows us to do work that benefits all Rust users, and in the case of the Interoperability Initiative, C++ users as well. Also, you can participate directly in discussions with the Rust community. In addition to financial support, we need to understand the challenges facing organizations. So even if you use C++ and haven't engaged with Rust at all, your perspective is valuable to building that better future. Finally, you can join the C++ committee. This is a cooperative effort. In order for C++ to evolve in a way that benefits interoperability, organizations that use C++ need to participate in the process. And it's actually easier than you might think. I'm happy to help with any of these, so feel free to talk to me after this talk or reach out via email. That's all I have for today, so thanks for listening. Here's my contact info, and I think I do have some time for questions, so I'd be happy to answer anything you have now. Yeah?
Hi. My question is around cargo. Am I allowed to ask that? So I understand like it was trying to follow the whole NPM strategy, but what we're seeing is like people are pushing every single day, and usually the most popular ones come on top. Is the Rust Foundation doing anything to try and like standardize what people push into cargo so that you don't have to dig through a needle and the haystack to find the needle?
Okay, so the question about Cargo, which is the standard package manager for the Rust programming language, and so the comparison was made to NPM, which is the node package manager, which is popular in the JavaScript community. And the question was, let me see if I sum it correctly, the idea was that NPM is sort of, indicating what packages are the best to use, and so that takes some of the burden off software developers to try to find, what particular library they want to use for their left pad needs. So I would say that in many ways Cargo is very similar to NPM in terms of the essential role it provides. It's a difficult situation in terms of governance because Rust has always been a very free and open community, and the idea that Cargo would take the role of sort of deciding what are the best tools to use for a particular purpose can easily cause a lot of discord in a community that prides itself on providing diverse solutions and encouraging people to customize their software choices. But at the same time, as more larger organizations are getting involved in Rust, the desire both to have a sort of standard set of best practices and sort of vetted libraries, as well as to do supply chain security, is definitely coming to the fore. There's currently a proposal for a so-called Rust extended standard library, which you can find if you search in the Rust RFC, which is the process by which Rust makes modifications to its library and the language itself that covers this. I'm trying to think of what the actual name of it, but if you search Rust extended standard library, RFC, you'll probably find it. And there's been a lot of active discussion. And there's definitely tension between, first of all, the huge amount of effort that's required to do vetting of all the libraries and their dependencies back to the standard library. But at the same time, as Rust is being used in more and larger applications, the need for supply chain security and the desire for new developers to not have to decide every minute detail of what their new project is depending on is becoming more important. I hope that answers your question.
Can I ask a follow-up?
Yeah.
So basically, the reason I was asking is, I tried to find out what this whole Rust thing is about, tried to start playing around, and it's not immediately clear if you're new to Rust what you should use. You have to like keep on searching or listen to a podcast and oh, there's something called Tokyo, and then you start using that. Oh, there's something called that. It's not very clear, hence why I asked that. But I think the standard library will probably be a good start. So check it out.
Thanks.
I guess two questions. One of them is, does the Rust Foundation have interoperability with other languages as well as C++? And the second one is, speaking only from experience, I don't know the whole picture, but even now I'm seeing financial institutions starting new high-performance projects that are not in Rust. Why do you think that is?
Okay, the first question is whether the Rust Foundation is supporting interoperability with languages other than C++. And to that I would say the initiative specifically that exists is focused on C++ interoperability, and there's a couple of reasons for that. The first is that interoperability with C is already very good. The second is that, as I described, there's not really that many systems languages, and it's primarily systems languages that really need this type of foreign function interface interoperability. There's lots of easy ways to do inter-process communication type interoperability, and those can be highly ergonomic and, like I was saying, even language agnostic. So if you don't care that much about performance and you're just trying to get your Rust process to interoperate with something that's written in Java or Python, there's lots of ways that you can go. The deepest need right now is for languages and applications that are at the systems level that need that performance and currently don't have the ergonomic solution, and that is overwhelmingly C++, simply because there's orders of magnitude more C++ out there in the world, and because C++, as compared to Swift or Go, which are the other main systems languages, C++ is memory unsafe by default. So the direness of moving new code is considerably higher there. And that's what led to the contribution from Google that started the interoperability initiative at the Rust programming, or at the Rust Foundation. And then your second question was, you're aware of high performance projects started among financial institutions that are not in, or that are in C++, is that what you said?
That are not in Rust.
Well, they're not in Rust. And hey, if they're in Java, like, great, it's memory safe already. If they're in Swift, that's unique, but also memory safe. But if they're in C++, then I have to think that that's because it's difficult to integrate into their existing systems without it also being in C++, or perhaps they're just not aware of the problems that I'm trying to publicize in this talk. So they should be here, or you should let them know.
I guess following on to that, like if you have an existing application which is already in C++, then how someone use Rust in that scenario? Because they would not want to move their entire current stack that they have, like the application which is already written in C++. So is it more for people who are starting out new projects that they should use Rust for? Or?
Oh, I mean, I absolutely think people starting out new projects should use Rust, but I think as a member of the foundation, we have to say that. But what you're talking about is exactly what the interoperability initiative is about. That's what foreign function interfaces are for, is taking a program that's already written in one language and you want to be able to introduce compiled code in a different language and have those, it's all part of the same program. Calling back and forth between the functions doesn't really matter what language it started in, as long as they are compiled down to functions which can call each other. Now, I'm glossing over a huge amount of technical detail here, and there's a lot of challenges to doing this well. There are a number of libraries that aim to make this more ergonomic and safer, but this is exactly the kind of use cases that we are trying to target. My background in Rust, part of it was working at Mozilla on the Firefox web browser, which is where the Rust programming language was originally incubated and developed. And gradually, parts of the Firefox browser have been written in Rust. Still, the majority of it is in C++ and probably will be forever, but major new components are completely written in Rust, and they call back and forth with the C++ code. And as a user, you would never know that. But it really benefits the security of the system in order to be able to write whole new components in Rust. What we're trying to enable with the interoperability initiative is making it much easier so the granularity of new code can be written in Rust much more easily. Right now, it's much easier to do if you've got like nice module boundaries. Like the Android operating system is a good example of that. They've been writing the majority of their new code in Rust for the last several years, and they've seen their memory safety vulnerabilities go way down. But part of that is that they benefit from a nice modular architecture where they can move whole components over. It's doing it in systems that aren't architected quite so nicely, where the interoperability initiative really aims to make life easier. All right. Seeing no further questions, appreciate your time. If you do have any more for me, feel free to reach out via email, or I'll be around the rest of today.